Okay, hello and welcome everyone. In this video, I'm going to talk about utility, which is a chapter title from Varian's Intermediate Micro textbook. So previously we've talked about the budget constraint, we've talked about preferences. Remember, we're interested in the consumer's problem, consumer's utility maximization problem, and the consumer's expenditure minimization problem, which we'll discuss much later. The basic idea is consumers are trying to do the best they can given the circumstances. The given the circumstances part we covered in the first lecture, budget constraints. The doing the best they can, we're actually elaborating on now. We introduced that idea through the chapter on preferences, and now we'll reinforce that with utility. So our central topic today is thinking about utility. I'm going to introduce the idea of the utility function. That's going to be our central tool for insights into consumer behavior. We want to know something about preferences and the assumptions underlying preferences because that's what consumers are actually going to have. We're assuming their underlying preference structure is going to be representable by the stuff we talked about in the previous lecture, although that's an intractable model and we want to be able to have something that's easy to work with. So we're going to model consumers' preferences using utility functions. So I'm going to introduce this here. And importantly, we'll think about calculating the MRS, the marginal rate of substitution, by examining the utility function, taking ratio of partial derivatives, which I'll talk about. So the concept of utility formalizes our consumer preferences. This is important because consumer preferences, though interesting, gives us a way to kind of talk about the consumer's comparison of how well they like particular bundles, can be really unwieldy to have to work with. So the idea is utility is one tractable way to describe preferences. Importantly, preferences give us a ranking of bundles, and we need utility to be able to preserve that ranking. So we're going to build a utility function. It's going to be an ordinal concept, meaning order matters, not a cardinal concept. So magnitude's not going to matter. It's going to be the order that's going to matter. Utility functions assign numbers to every possible consumption bundle, so more preferred bundles get a higher number than less preferred bundles. So if I prefer bundle X to bundle Y, then the utility generated from bundle X has to be higher than the utility from bundle Y. Actually, I wrote this with a weak preference. If I weakly prefer bundle X to bundle Y, then my utility is weakly higher from bundle X than from bundle Y, right? This is going to be our requirement that whatever is the underlying preference relationship is reflected through the utility function, though there's many utility functions that can represent a given preference shape. So if a bundle X is weakly preferred to bundle Y, any valid utility function must assign a number at least as high to X as to Y. This is elaborating on what I just said. We can have a lot of different utility functions that preserve the same underlying preference structure. So here's my example. Suppose talking about like 1 unit of coffee, my utility is 10, 1 unit of cookies, my utility is 0, and 1 unit of oatmeal, my utility is -5. All I can see as a result of this is that, well, I prefer that 1 unit of coffee more than the 1 unit of cookies, more than the 1 unit of oatmeal, and I prefer coffee to oatmeal. I can't say something about, the relative magnitude. I can't say something like, I like coffee way more than I hate oatmeal or something like that. No, that's not how that works. Matter of fact, I actually like coffee and cookies and oatmeal, and this is perfectly consistent with those underlying preferences for myself. Why? Because we only care about the rank of utilities. The actual numbers are less interesting. So this utility function, this different utility function, is going to give me the same preferences. All this is going to say is that I like coffee more than I like cookies, more than I like oatmeal. I don't say anything like, you might be tempted to say, Ben hates oatmeal. Nope. All we can say is the numbers, the actual numbers are less interesting. All we can say is something about the ranking. So these two utility functions are all giving us the same information, which is my relative ranking of bundles that consist of 1 unit of coffee or 1 unit of cookies or 1 unit of oatmeal. To this end, we can introduce the concept of monotone transformations. So a monotone transformation is just going to be a function we can apply to the utility function. It's a function of a function. Think of like compositions of functions, such that the underlying preference relationship remains the same. All right? And so for this, I'm actually going to step aside for a second into my other set of lecture notes. This is going to be puppy study break. How about that? I thought I was clicking on my extra set of lecture notes. I'm instead clicking on puppy study break. So where did my extra set of lecture notes go? I was convinced I had these all ready to go for us, and seemingly have not. So what do we have? Oh, here we go. Here's my extra set of lecture notes. Sorry about that. Here I thought I had everything set up and ready to go. This is the one that I've called Econ 401 lecture note 4B, and it's for this purpose right here. To ruin my video, just make a fool of myself. That's what it's for. No, it's for this right here. So when we're talking about monotone transformations, the idea is we're taking a function of a function. If this is my preference relationship, x is strictly preferred to y, and g of x is greater than g of y, where g is a monotone increasing function, then this v of xy equals g of u of xy will be a utility equivalent utility function. It's going to preserve the same ranking. For instance, here's some examples and non-examples of monotone transformation. If my utility from bundle x is 10 and my utility from bundle y is 2, let's think about the doubling function. So I'm just going to construct this new function. V of this dot right here just means argument. So this just is a lazy way of saying x1, x2 is equal to 2 times u of, lazy way to say x1, x2. So if I double my utility, right, this becomes 2 times 10 is 20, double this, 2 times 2 is 4, all right? This is telling me utility function v preserves the same underlying relationship. Yes, the doubling function is a positive monotone transformation. The negative function is not. Suppose I take the negative of my utilities, I make this negative 10, I make this negative 2. There's a problem. This right here, this preference structure is saying I prefer bundle x to bundle y because my utility for x is 10, which is bigger than 2, which is my utility from y. This right here is actually saying I prefer bundle y to bundle x because minus 2 is bigger than minus 10, right? So this would not be a monotone transformation. All right, so that's all I wanted to do. Going back to the slides talking about monotone transformations, I've got some other examples, I got some other non-examples that can get real confusing real quick. So let me fix this. Here's how to not be confused by monotone transformations. If you're trying to determine if you have a monotone transformation, the question is, does it preserve the underlying rank order of bundles? Test a couple, find out if it does, check the natural candidates, some that involve negatives, 0, and positives. If it preserves the underlying ranking ordering, you've got a monotone transformation. If it doesn't, you don't. That's all we need to care about. There's really one main place where we'll see this, and this is taking a positive monotone transformation, taking the natural logarithmic transformation of the Cobb-Douglas utility function. And there's a couple other places in the course where you could do this to simplify things. Monotone transformations are designed to make our lives easier. You want to be careful, and as you're going over this first time, as when I say make my life easier, it sounds like you're making my life way harder. Right, okay, so we want to simplify things down. The point is, go back to what I just said before, how do you know if you have a monotone transformation? It's if it preserves the underlying rank ordering of bundles. When would you take a monotone transformation? Well, if you can think of one that's going to make the math easier. In a lot of cases, you won't be able to do that, but in many cases you will, and then you'd want to do it. And this becomes much more important for applied economics, for thinking like the economics of entrepreneurship, thinking about, I mentioned sorry, I kind of trailed off, my economics of entrepreneurship course. We don't actually do this, we don't actually do it, but if you were doing the econometric analysis, you might find it useful to work with logs quite a lot. Anyway, so the next thing I want to talk about is indifference curves and utility functions. We already introduced indifference curves, and it turns out indifference curves are one thing from the preferences lecture we're going to continue to use, because it turns out the level sets of our utility function are going to be indifference curves. Indifference curves are going to be the level sets of the utility functions we're going to work with. By level sets, we mean like cross-section. Our utility function, this is a multivariable function, right? So this is actually like z is equal to u of x1, x2. X3 is equal to u of x1, x2 equals x1 times x2. So kind of develop that idea a little bit later on, but the link between indifference curves and utility functions is indifference curves are the level sets of the function, right? That's this. All right, so what you want to do is you want to fix the level of utility and find all combinations of x1 or x2 that provide a given level. And in doing so, you will have found an indifference curve, right? All combinations of x1 and x2 that give the same utility. Wait, utility is going to give me my ranking of that bundle. If they give me the same utility, that means I like those bundles the same. All combinations that give me the same level of utility must, being that that's consistent with our definition of an indifference curve, must be on the same indifference curve. Changing the fixed level gives us different indifference curves. We can draw these out. So suppose I take this utility function. This is actually our Cobb-Douglas utility function, where I multiply my amount of good 1 times my amount of good 2. If I set this equal to some utility level, k, and then solve for x2, think of x2 as like y, think of x1 as like x. This would be like y is equal to k over x. Right? And this is a function we can draw in 2 dimensions. This is going to be my level sets of this utility function. And for a different k, we'll get higher indifference curves. That's this picture here. Right? That's all this is doing. Giving a different k is going to give us a higher indifference curve. And then think about this. Think about which bundles are going to be on, say, k20. It's going to be where x1 is 4, x2 is 5. Or where x1 is 5, x2 is 4. Or x1 is 20, x2 is 1, or x2 is 1 and x2 is 20 and x1 is 1, right? All the ways to multiply to get 20 because k of 20 is equal to x1 times x2, right? That's what the level sets of the utility function are giving us, and that's what our indifference curves are giving us. We are going to represent our utility functions graphically using level sets, using our indifference curves, because that's going to help us draw pictures to solve our utility maximization problem. Here's an example. Bob has the utility function, Cobb-Douglas utility. Bob's indifference curve passes through 32 apples and 8 bananas. It'll also pass through the point where he consumes 4 apples and how many bananas? All right, so we have to go ahead and find Bob's utility level. So Bob's utility level from 32 apples and 8 bananas is 256. To stay at that level but consume 4 apples, Bob needs 64 bananas, right? Okay. So when we're coming to utility functions, there's going to be 4 main ones that we're going to deal with. Perfect subs, perfect complements, Cobb-Douglas, which we just saw, and then quasi-linear. For perfect substitutes, what matters to the consumer is the total amount they have. So for instance, the amount of good 1 I have plus the amount of good 2 I have is my utility. So if I view Coke and Pepsi the same, it doesn't matter if I have 5 cans of Coke and no Pepsi, or 0 cans of Coke and 5 Pepsi. They're going to be the same. All that matters is the total amount I have if they're perfectly substitutable, or 2.5 and 2.5. That doesn't make sense. What if it's 2,500, right? Then, so anytime you have decimals, you can just scale up by multiplying, and you can make it so that you don't have decimals anymore. There's a more general form for perfect subs. This would be, suppose the contribution to my utility is different for good 1 and good 2. We call that marginal contribution to my utility, my marginal utility. A would be the marginal utility of good 1. B is the marginal utility of good 2, right? If I increase my amount of good 1 that I have, my utility rises by A. If I increase the amount of good 2 that I have, my utility rises by B. It turns out also, if I take the derivative of this function with respect to x1, it's just A, right? The derivative of like 2x is just 2. So if this is 2x1, the derivative with respect to x1 is just A, right? Or 2x1 would be 2. The partial derivative with respect to x2 is going to just be B. So partial derivatives, depending on math background, might seem a little bit scary at first. Basically, what you're doing is remembering our standard utility rules, right? If you're taking the derivative, taking dy dx, and the function has an x in it, you're going to take the derivative with respect to that function as you know how. If the function doesn't have an x in it, the derivative is just 0. That's what we do with partial derivatives, right? So if I take the derivative, du dx1, it's A. If I take the derivative of this thing, du dx2, it's B, because this is a constant when I differentiate with respect to good 2. All right, A and B measure the value of the goods, x1 or good 1 and good 2, to the consumer. It's the marginal contribution. The slope of a typical indifference curve is going to be minus A over B, right? It's going to be the ratio of marginal utilities. This is actually the MRS. Marginal rate of substitution for the consumer is going to be the negative ratio of the marginal utilities. Although I'll have a note in a second. We'll just talk about this in absolute value very often. With perfect complements, these are goods that have to be consumed together. So the general form is going to be my utility is whichever is the smaller of AX1 and BX2. So here A and B are typically positive and indicate the proportions in which the goods are consumed. Think of like a recipe. You need so many cups of flour, so many cups of chocolate chips or whatever. Think of left and right shoes. Then alpha and beta are going to be 1 for most people. And that's what this is giving us. So perfect complements. So perfect subs is giving us downward sloping indifference curves with a slope of minus A over B. Perfect complements are giving us indifference curves that look like right angle corners. Quasi-linear utility are these vertically shifted versions, right? So the height of the indifference curve is going to be some function plus of x1 plus some constant. Quasi-linear just means you've got a linear component and a non-linear component. So we're assuming x2, that's linear. Coefficient here is just 1. V of x1 we're assuming is non-linear. Maybe it's ln of x1, maybe it's x1 squared, square root of x1, whatever. So the utility function is linear in good 2, possibly non-linear in good 1, and then that makes our quasi-linear utility. And then for Cobb-Douglas, we have, this is a more general form of what I had before. It's the amount of good 1 to the c power times the amount of good 2 to the d power. And previously I had D and C and D were equal to 1. But Cobb-Douglas preferences give us a good example of well-behaved preferences where we have more is better than less and averages are preferred to extremes. So here's my graph for quasi-linear utility. And so these are level sets of my quasi-linear utility function. Here's my graph for Cobb-Douglas for different levels of D, or C and D, for different levels of those exponents, right? And so this is just looking at level sets. These are our nice convex, well-behaved preferences. And I mean for these to asymptote to the axis. These are just graphics right out of Varian. All right, so here's why one of the reasons why we talk about monotone transformations. You can take a monotone transformation of Cobb-Douglas preferences. Now remember I said the slope of the indifference curve is going to be the marginal rate of substitution. All right, so the slope of the level set is going to be the marginal rate of substitution. That's going to be the ratio of partial derivatives with respect to good 1 and good 2. That's easy if my utility function is perfect substitutes. What about for Cobb-Douglas? Well, I have to take the marginal utility with respect to good 1 divided by the marginal utility with respect to good 2, which means I have to take the derivative of this thing. I'll show you that a little bit later on, but trust me, or remember, it's much easier to take this derivative than this one. Right? So here I'll take a natural log of this utility function. When I take the natural log of this function, what this is going to be is the log of something raised to the power is just that power times the log of that something, if you follow that. And then the log of a product is the sum of logs. Right? The log of the product is the sum of logs. So this is the log transformed representation of this function. The derivative, the partial with respect to x1, the derivative of ln of x is just 1 over x. So the marginal utility of good 1 is just c over x1. The marginal utility of good 2 is just c over x2. And then those ratios, it cleans up really nicely, one over the other. So that's getting ahead of ourselves, but this is the monotone transformation for a Cobb-Douglas utility. So now I want to talk about the relationship between the MRS, marginal rate of substitution, and utility. So here is the marginal rate of substitution and utility. It's the slope of the indifference curve. Well, for a convex function, it's the slope at that point. Right? And so here is my nice well-behaved Cobb-Douglas, presumably utility function, corresponding to a utility level of k. Here is going to be the MRS at that point. It's the slope of the line tangent to the curve. Right? All right, so suppose the consumer is currently at some bundle. We're interested in studying how the consumer's utility changes when they get more of good x, holding consumption of good y constant. So this would be the marginal utility with respect to x, or MUX. So that's how utility changes with respect to changes in x. That's like my utility coming from x plus a little bit more x, holding y constant, minus my original bundle, divided by my change in x. This is nothing other than the rate of change in utility, delta U, associated with small changes of good x, represented by the change in x while holding y constant. We can do this for good 2. So from this ratio, we see in order to obtain the change in the utility associated with small changes, we just multiply the change by the marginal utility. That's just like manipulating this. So To get my change in utility, I can just get MUX, which is the change in utility coming through X times the change in X. So move this, delta X times MUX is this line right here. So delta X times MUX is my change in utility coming through good X. And then similarly, I can do this for good Y and then get my total change in utility. So here's my change in utility coming through Y. This looks exactly like this. This is just for Y. So just as I got this statement from this, I can get this statement right here from the work above. This is just saying, what's my change in utility, my marginal utility of Y? How is my utility changing when Y changes? So here's hold the composition of my bundle, the amount of X in my bundle the same, but change how much Y I have. Okay, so it's giving me my change in utility coming through isolated by the change in Y. And so it's saying my change in utility coming through Y is going to be my marginal utility of Y, how much that additional Y is worth to me, times the change. How much additional Y did I get? I'll show in a second, if we think of these as infinitesimally small, that's redundant, X are changes, then we can do calculus. So we already know MRS gives us the slope of the indifference curve going through the bundle. It's the rate at which the consumer is exactly willing to substitute an amount of Y for good X. So this gives us a way to get our MRS. We get it through marginal utilities. So consider the changes in consumption if we simultaneously change X and Y, but stay in the same indifference curve. So we want our utility not to change. So the change coming through X is going to come through marginal utility of X. The change coming through Y is coming through the marginal utility of Y. My total change I want to be, well, I want to keep that at 0, but here's going to be my marginal change in utility from X, marginal utility of Y. One of these will be negative if I'm not changing my utility overall. That's going to be equal to 0. But anyway, we know MUX and MUY, and we know change in X, our utility coming through X, and change in utility coming through Y. We can represent this as my marginal utility of X times the change in X plus my marginal utility of Y times the change in Y gives me my total change in utility. If I don't want to change my total level of utility, if that's 0, if this is 0 right here, then I can solve this. I can solve this for delta Y over delta X, and that's just going to be the ratio of marginal utilities. That is why a couple slides ago I said our MRS for perfect substitutes utility was just A over B, the marginal utility of X with respect, or divided by the marginal utility of Y. Notice also delta Y over delta X, this looks a lot like dy dx. That's a derivative. That's a slope of a line. Sure enough, my marginal rate of substitution is going to be the slope of the indifference curve, delta Y over delta X, and my marginal rate of substitution is going to be the negative of marginal utility of X divided by marginal utility of Y. So we have, as a result, my marginal utility of X is going to be, or my marginal rate of substitution is going to be MUX over MUY. Very often, I'm going to forget that negative sign, and that might bother you. Don't let it, right? Here's why. Varian has the following comment, which I want to read because this comes up a lot. The algebraic sign of the MRS is negative. If you get more of good 1, you have to get less of good 2 in order to keep the same level of utility. However, it gets tedious to keep track of this pesky minus sign, so economists generally refer to the MRS by its absolute value. We'll follow this convention as long as no confusion will result. That is important. So I am going to refer to the price ratio as positive, though we have a downward sloping budget constraint. And I am going to refer to the MRS as positive, though we know indifference curves are also downward sloping. Why? Well, it's not going to matter because of this. And also, ultimately, we're going to compare the price ratio, PX over PY, to MUX over MUY to find the optimal bundle. What I just gave us, that's our tangency condition. We'll do that in the choice lecture thinking about optimization. And if they're both negative, those signs cancel. Both becomes positive. And if they're both positive, we're already on the right track. All right, so here's the calculus version. So the utility function can be used to measure MRS. Given a particular bundle, the consumer's MRS is equal to the slope of the line tangent to the utility at that bundle. The MRS depends on how much extra utility is enjoyed by consuming a little more of the good. So suppose I have utility function, X is cookies, Y is coffee. The additional utility I get from consuming the last unit of good, cookies, is my marginal utility of that good, cookies. So more formally, MU1 is going to be my marginal utility of cookies, where good 1, so 1 means the first argument in this function. So you're like, 1, this should be X. No, MU1, this is the first argument in the function, so I'm going to have MU1 du partial du dx is my marginal utility of cookies. Cookies was X. And marginal utility of good 2, this is referring to the second argument in this function. Du dy is my marginal utility of coffee. All right. So far we've defined we've defined a utility function and two marginal utilities. Marginal utility is just the partial of the utility function with respect to that good. So du dx, or the partial derivative of the utility with respect to x, gives me my marginal utility of x. Partial derivative of the utility function with respect to y gives me my marginal utility of y. The total derivative, the total change in utility, is going to be the partial with respect to x times the change in x plus the partial with respect to y, change in y. We can rewrite this using our marginal utilities. Du dx is just mux, and du dy is just muy. And then this dy dx is just going to be the slope of the indifference curve, right? We already defined MRS is equal to the slope of the indifference curve. Now we have MRS is equal to dy dx is equal to the ratio of the marginal utilities, right? This is exactly what we did before. I just replaced it with calculus. We've just now done this twice. All this is to say, you can find the marginal rate of substitution by taking the ratio of marginal utilities, which is nothing other than the partial derivatives of the utility function. From the preceding, the MRS is just the ratio of marginal utilities. This is important. It's how we find the MRS. The MRS will be the ratio of marginal utilities themselves, nothing more than the partial derivatives of the utility function. And I'll walk through the differentiation in the examples we'll do. Here's some more examples. So for perfect substitutes, the marginal utility of x, I said this before, it's just the derivative with respect to x, it's a. Marginal utility of y is just the derivative with respect to y, it's b. So the ratio of marginal utilities, the MRS, it's just a over b. For perfect complements, I don't know, I kind of even don't want to go over this. It doesn't really make any sense because the thing's non-differentiable. You've got a vertical portion, you've got a horizontal portion, you've got a kink. Let's even kind of forget about, I don't know, I kind of regret having this in here. So this is going to, I know this is going to derail somebody. Somebody's going to try to focus on this and ask me a bunch of questions, and it's not worth worrying about, because this isn't something I'm going to ask us about. The point is my utility. So let's think about this for a second. What's going on? My utility is going to be whichever is the smaller of these things right here. So if the smaller is ax, is the ax portion, my amount of x times a, if that's smaller than the amount of y times b, then my utility is driven by the ax side, which is why I need to have the marginal utility of x. If the smaller of the two is b, then my utility is coming from, by, then my utility is coming from by, right? So then my marginal utility has to come through the smaller part, right? If this is smaller, my marginal utility of y is going to be b, if my utility is actually being driven by by. If not, then it's going to be 0 because my utility is driven by the other part. So if you follow that, good. If not, let's go to the next part of the video. Right? Seriously. All right, so here is Cobb-Douglas, and now we need the marginal utility of x and marginal utility of y. This is one we're going to be doing a lot, and so this part's important. So here's my marginal utility of x for Cobb-Douglas. I'll take this partial derivative with respect to x. So I'm going to take this derivative, you'll bring down the power, right? So a comes in front, bring down the power. And it'll reduce the exponent by 1, and then this y is a constant with respect to this differentiation, so it comes along for the ride. So my marginal utility, my partial derivative of this utility function with respect to x is going to be ax, a to the x1. This yb comes along for the ride. Now let's do that derivative with respect to y. This b has to come out front, reduce this power by 1, so it's going to be bx to the a, y to the b minus 1. This is so where do people screw up? Sometimes you forget about this yb and you forget about this ax to the a. So don't do that. Don't forget that. So remember that it's coming along for the ride. All right, now we need our ratio of marginal utilities. So it's going to be mux over muy. And so things are going to divide, things are going to cancel, and we're going to end up getting a over b is equal a over b times y over x. So I'm going to say two things really quick, really important. When you have Cobb-Douglas utility, the MRS is going to involve a y over x or an x2 over x1 if this is x2 and if this is x1 and this is x2. It's always going to be that way. If you get a Cobb-Douglas marginal rate of substitution and you have x over y, did something wrong. If you have x1 over x2, you've did something wrong. Or if you have a y and no x, or an x and no y, you've done something wrong. So for Cobb-Douglas, we're always going to have a y over x, and then this a over b is going to be governed by these exponents. Right? Okay, so where is this coming from? Think about this divided by this. Remember how we divide exponents. If it's got the same base, you subtract the denominator from the numerator. So it's going to be a minus a minus 1 minus a. So a minus 1 minus an a is going to be a minus 1. A to the minus 1, 1 over something raised to a negative power, bring that to the numerator, right? So we're going to have, let's see, so we're going to have x to the a minus 1 minus minus a is going to be x to the minus 1. X to the minus 1 is already in the numerator, so we need to bring it to the denominator. So that's why we get over x. For y, now we've got, let's see, we've got y over b minus y over b minus 1. This is going to be b minus b is 0, and then we're going to get a minus, and then we're going to have this minus 1. That's going to bring that y into the numerator. Okay, so that's where this MRS comes from. Probably have to write that out. I would write this out, but I don't have my pen and anything like that. So here is the more straightforward way to see this. You're like, oh, that was really complicated. I don't want to deal with that. Okay, you don't have to. You can take a monotone transformation. So let's take the natural log of the Cobb-Douglas. It's this, right? If I take the natural log, it's going to be a ln of x plus b ln of y for the reason a couple slides before. The marginal utility of x is going to be a over x because the derivative of this with respect to x is 1 over x times 1. A is going to be a over x. The derivative of ln y is 1 over y times b is b over y. The ratio of these things is going to be a over x times b over y. Derivative or when you divide one fraction by another fraction, it's the same as multiplying the first by the reciprocal of the second. So this is going to be a over x times y over b. Oh, that's this. A y over bx. All right, so I mean, clearly that was way easier than this, wasn't it? So that's why people take monotone transformations of Cobb-Douglas. Now, interestingly, and something that's really important, is if you evaluate at a specific bundle, you will get different utility values, right? So evaluate at a bundle, like let's assume the exponents are just 1, right? And evaluate at the bundle of like, I don't know, like 10, 10 or whatever, you're going to get a different value for this versus this. That's okay, right? Of course, we're going to return different levels of utility. Remember, the magnitude's not what we're comparing. It's the ranking of bundles. So if you compare two bundles, if one's preferred to the other in this utility function, it's got to be the same. It's got to be the same preference with this one. The MRS, however, the utility levels are different. The MRS is the same. That's what the monotone transformation does. The MRS of this function is the same as the MRS of this function, right? That's what our monotone transformation is getting us. It's telling us we have the same preferences, meaning we're willing to trade off y for x at the same rate because we have the same preference structure. Okay, so here we discussed utility and utility functions, discussed the relationship between indifference curves and utility functions, considered our 4 examples of common utility functions, and introduced marginal utility and the link to MRS. And I sure hope you enjoyed this video.